Before I discuss a classic tool for outlier detection, I'll begin with a story to develop some intuition. There was a dad who loved watching soccer on TV with his son, and he wanted to take him to see a game in person. But the boy got bored during low-scoring games and didn't want to go to a game if no one scored. The dad explained, "Look, the average number of combined goals in a game is 2.62. He grabbed his laptop and entered 2 lines of code. Then he said, "Our chance of seeing a game when no one scores is only 7%. The Poisson object here represents a Poisson distribution, which expresses the probability of a number of rare events happening if they occur at a constant rate. From a Poisson distribution, we can obtain the probability of any number of goals being scored in a game, and I plotted those probabilities up to 9 goals. So we actually have about the same chance of seeing 5 goals scored during a game as we do of seeing no goals. And at least 3 goals are scored at half of the games. It seems pretty far-fetched that a math function from the Age of Enlightenment could accurately predict the number of goals scored in a soccer game today. So I downloaded some soccer data and prepared it for analysis. Here are the average number of combined goals scored per game during each of 5 consecutive seasons. The average for all games was 2.62, and we can see here that the rate of goals scored during each season was near constant, so Poisson should be fairly accurate. Here's the actual distribution of goals per game during the entire 5-season period. And here's the same plot along with predictions from a Poisson distribution. The shapes of the actual and predicted distributions are amazingly similar. Remember, we generated these predictions using only one value, the average number of goals scored per game. So just how are these mystical probabilities calculated? Here's the formula. This is how we calculate the probability of observing k events, where lambda is the mean rate of occurrence. So let's compute this 7.5% probability. 2.62 is raised to the 5th power times e to the negative 2.62 power divided by 5 factorial. This black box function gives us 7.5%, which uses our formula under the hood. So how can this simple equation be so darn predictive? I should mention that it's applicable to a lot more than just soccer. The Poisson distribution is well suited to handle independent or weakly dependent rare events that occur at a constant or near constant rate, like these examples. The real magic behind this formula is the incredible constant E. So what is E? I'm sure you're familiar with pi. Well, E is an irrational number like pi whose non-repeating decimal digits never end. Pi is defined with geometry. If we say that any circle's width equals 1 unit, like 1 inch, 1 yard, or 1 mile, then the distance around the circle is pi units long, or approximately 3.14159. So pi is useful for computing values like the volume and surface area of shapes that contain circles. Unlike pi, E is not defined using geometry. While studying continuously compounding interest, Bernoulli computed E with this limit as n approaches infinity. If we use a sufficiently high value for n, we can compute a great estimate for E. Euler defined E with the sum of an infinite series. If we add up just the first 18 terms, we again get a great approximation. So whereas pi is based on the shape of a circle, E is a seemingly magical number that exists in nature and indicates how fast things grow. Here's another fantastic discovery from the Age of Enlightenment. So let me get this straight. raising a number with an infinite amount of decimals to the power of another number with an infinite amount of decimals times the square root of -1 equals -1? What in the world? This is the best explanation I could come up with. The world is governed by natural laws whose regularities can be discovered by the methods of science. In other words, nature's laws can be expressed in mathematical terms. Finally, onto the topic of outlier detection. An outlier is a data point that is significantly different from normal values, and a Poisson distribution can show us if a value has an extremely low probability of occurring. You can provide outliers to a domain expert who can analyze them to determine if they are anomalies or just noise. Anomalies are potentially dangerous and need to be acted upon. I'll demonstrate how to use a Poisson distribution for outlier detection. There are several ways to log into the Snowflake platform. You can enter via Snowflake's interfaces, their Web UI and their CLI. You can call APIs from within programming languages, or you can use database connectivity drivers. This account usage view can be used to examine login attempts during the past 365 days. And this table function can be used to monitor logins in near real time. Say we're interested in login attempts that failed because of incorrect username-password combinations. I'll run this query to compute the average number of these kinds of errors that occurred each day. Let's say there were 1.75 errors per day. I used a Poisson distribution for this error rate to show the probability of 0 through 10 errors occurring each day. The probability of there being less than 6 errors is 99%, so we'll trigger an alert if 6 or more errors occur in a day. At the end of the first day, several errors occurred during the last 3 hours. But since the total was below our threshold of 6, no alert was triggered. At the start of the second day, 5 more errors occurred, but once again the daily total was below our alert threshold. Instead of examining the number of errors after a fixed period of time, like after 24 hours, we can examine the period of time it took for a fixed number of errors to occur. Our threshold is 6, so once there's been 6 errors, we can compute how long it took from the first error to the last and trigger an alert if it was less than 24 hours. The rate we're using is 1 3/4 errors per day, but the Poisson distribution doesn't really care what our unit of measure is, so we can use hour instead of day. Here are the probabilities for our new hourly mean. The likelihood of an error occurring twice in an hour is just 1/4%. Since the error happened twice within this hour, we should immediately send these outliers to a domain expert for investigation. I hope you enjoyed learning about how a math tool from hundreds of years ago is still very useful today.